Okay, we'll start the session now. So in the last class, we were talking about the classification of the embedded system, as well as the typical embedded system as well, how the embedded system looks like. So, okay, we have the system code, which is not independent, or also this system core is connected to either input output ports or the memory, either other supporting integrated circuits as well as the embedded firmware. What is this? The input output source. They are also called as the sensors, right? And output ports are also called as the actuators. And whereas the system core is also connected to memory, where which is going to store load and store the values, right? uh, so which is basically used to hold the values temporarily. And also we have the embedded system and other integrated circuits are also connected to the system code, right? And what are the things we have in the embedded system? We have uh, the different categories of the embedded system. The microprocessor, we have controllers, digital signal processing, right? And also application specific integrated circuits, right? And programmable logic devices as well, and commercial off-the-shelf components are also called as the codes things, right? So we have seen all these things, general purpose and the domain specific processors, right? And the processor, microcontrollers, we have seen it, and the digital microprocessors as well. So digital signal processor as well, right? So only thing is that microprocessor, there is a resemblance between the microprocessor and the microcontrollers. Microprocessor are built for some specific purpose, for general purpose thing, and they have the what you call it as a predefined instruction set of instructions. And whereas microcontroller is highly integrated chip that contains everything, right? CPU, scratch card, RAM, special and general purpose registers, on chip RAM, and flash memory for program storage. Everything they have it, right? That's the difference. And to have that, there is one more thing called as a digital signal processors, which is powerful special 8 power 16 or 32-bit microprocessor designed specifically to meet the computational demands and power constraints of today embedded video and audio as well as the communication applications. This is specially meant for what you call it as to, to meet the computational demands. They are basically used to find some of the products, the product of the sums and the convolutions and fast Fourier transfer and such. And even with the matrix multiplication, large matrix multiplication, for such application, you are using digital signal processors, right? So this is how your the component. This is the basic unit key units of the DSPs. We have seen all these things, right? And there is a difference between RISC and the CISC processor. We have also seen it, and RISC is making use of the what you call it as Harvard architecture, whereas CISC is making use of either Harvard or the Van Neumann architecture. And we have seen the difference between these two. So what is the difference between Harvard architecture as well as the Van Neumann architecture? So let us look at one more important aspect of any microprocessor or the microcontroller, and even with the DSPs, that is a digital signal processing. So they are called as a big ending and the little ending processors or the controllers. What is the ending is specifies the order in which the data is stored in the memory by processor operation in a multi-byte system. How the how the or the order in which the data is being processed or it is stored in the memory by the processor operations in a multi-byte system. How the data is being stored in the memory, it is called as the endedness, right? Suppose the word length is 2 byte, then data can be stored in memory in two different ways. That is higher order of data byte in the higher memory and the lower order of data byte just below higher memory. That is called as the little ending. There is higher order byte will be stored in the higher order memory and the lower order byte will be stored in the lower memory. Whereas something is called as the big ending, which lower order byte will be stored in the higher memory, whereas the higher order byte will be stored in the lower memory. So, higher order byte will be stored just with the higher memory. It is called as the big endian notations or the big endian thing, right? So just try to understand what is that high order of the data byte out at the higher memory and lower order of the data byte at a location just below the higher memory. It is called as the little endian, right? It is stored in the things and lower order of the data byte at the higher memory. It is stored in the higher memory and the higher order of the data byte at location just below the higher memory, right? This is how you are storing the things, right? In case of the little ending, you're storing the higher order byte in the one memory location. Below that, you are storing the lower order byte. And in case of the big ending, you're storing the lower order byte in one memory location, and just below that, you are storing the higher order bytes. That is called as the big endian notations, right? Little endian is used by Intel 86 processors, whereas big endian notation has or the big endian notation can be used by Motorola 68000 series processors. So how the little endian and the big endian works? Little endian means lower order byte of the data is stored in memory at the lowest address and the higher order byte at the highest address. The little end comes first, right? That little endian. For example, a 4 byte long integer for byte 3, byte 2, byte 1, and byte 0 will be stored in the memory as shown below, right? So that is at base address plus 0, we are storing byte 0. At base address plus 1, we are storing the first byte. At base address plus 2, we are storing byte number 2. And base address plus 3, we are storing byte number 3. That is, lower order byte will be stored in the lower memory location, whereas higher order byte will be stored in higher memory location. We call it as a little endian notations or the little endian notation. And the processor which is making use of this one we call it as the little endian processors or the little endian controllers. Look at the organization here. So if it is making use of the base address is set to 20,000 hexa, right? And so the 0 will be stored at location 20,000, right? And the byte 1 will be stored at 20,001, that is base address plus 1. And byte 2 will be stored at 20,002, and the byte 3 will be stored at 20,003. In other words, uh, lower order byte of the data is stored in the memory at the lowest address. This is the lowest address. 20,000 is the lowest address, and 20,003 is the highest address. Order byte at the highest address. That is, the higher order byte will be stored at the highest byte. For example, a 4 byte long integer, that is byte 3, byte 2, byte 1, and byte 0 will be stored in the memory as shown below, right? This is how your little endian notation works. Big endian, right? It is just the reverse of that. Higher order byte will be stored in the lower order memory locations, and the lower order byte will be stored in the higher memory location. That is how. So big endian means the higher order byte of the data is stored in memory at the lowest address and the lower order byte at the highest address. That is the big end comes first. That's why it is called as a big endian. Look at this. You look, compare this one with this, right? The byte number 3 will be stored at 20,000. So whereas in case of the little endian, byte 0 is stored, right? 20,000 at base address 20,000 we're storing byte number 3, and 1 we're storing byte number 2, and at 20,002 we're storing byte 1, and at 20,003 you're storing byte 0. In other words, the higher order byte will be stored at in the lower memory location, and the lower uh, byte will be stored at the higher memory location. 20,000 is the lower memory location, whereas 20,003 is the higher memory location, right? So big endian means the higher order byte of the data is stored in memory at the lowest address, and the lower order byte at the highest address. That is the big end comes first. For example, a 4 byte long integer, byte 3, byte 2, byte 1, and byte 0 will be stored in memory as shown below, right? This is how your big endian notation works. That is base address plus 0. So that is stored at the lower memory location, and below that we are storing base address plus 1. We are storing the next one, that is byte 2. Below that we have byte base address plus 2, so we're storing byte number 1. Below that we have base address plus 3, where we are storing byte number 0. That is how you're going to work, you're going to see. So just remember that in case of the little Indian notation, the lower order byte of the data will be stored in lower memory location, right? Higher order byte will be stored in the higher memory location. Whereas in big Indian, higher order byte will be stored in the lower memory location, whereas lower order byte will be stored in a higher memory location. So that is how you are. And how the load and store operations, and what do you mean by the instruction pipeline, how they are used in different processors. The memory access related to operations for or performed by the special instructions called as load and store instructions. If the operand is specified as a memory location, the content of it is loaded to a register using the load instruction. So that is, you are moving a value, or you are moving the value specified by an address into a memory location, so into a register. That is, whatever the value you have at a given memory location or at a given address, that will be moved to a register. Or the next one, it is a store instruction, which is nothing but you are storing a data from uh, the specified memory location. Moving the data from a register, a specified register, to a specified memory location. That is called as the uh, that is called as a store instructions. The concept of load and store architecture is illustrated with following example. If suppose X and Y are Z or memory location, then we want to load contents of X and Y and store the result of in location Z. Under the load store architecture, the same is achieved with four instruction as follow. Right? Right. What you are doing is that, so there is an example here given me, but the load instruction in the sense that you are moving the data from a given memory address into a specified memory, a specified register, right? And stored in the sense that you're moving the value or the data from a specified register to a memory location. Okay, so we have three values here. So memory locations X, Y, and Z, or memory location, and we want to add. So we want to add uh, the contents of X and Y and store the result in location Z. Under the load store architecture, the same is achieved using something. That is, what is the problem definition here is that we want to load the value of X into one register, Y into another register. Contents of those two registers has to be met, and whatever the result you have, so that will be stored in another register, and the contents of that will be stored into a memory location. That is what the meaning here. So look at this. I'm moving the contents of X, right, a memory location, into a register called as R1, right? The contents of X will be moved to R1, and the Y it's a memory location. The value of Y will be moved to a specified register called as R2, and the contents of R1 and R2, which is nothing but X and Y value, will be added, and the result what you get, that is X plus Y. So whatever the result you will get, it will be moved to register R3. It will be moved to register R3, and from R3 you are storing it into a memory location called as Z. A memory location called as Z. So here is the instructions here. That is from 0 X, which will be moved to R1, which will be moved to R1. So Y value will be moved to R2, right? So R1 contains the value of X and R2 contains the value of Y. And so once it is done, the yearly will calculate the addition of these two. So okay, so addition of the contents of these two registers, that is R1 and R2, and whatever the value will get it, that will be moved to register R3. It will be moved to register R3. That is R3 we have. From register R3, you are moving it to a memory location called as Z. You're moving it to a memory location Z it is. This is how you can achieve the load and store instruction as well as the instruction pipelining. The first instruction, look at this. Load R1 comma X loads the register R1 with the contents of memory location X, right? The contents of X, memory location X will be moved to or loaded to R1. The contents of memory location Y will be loaded to R2, and adds the contents of register R1 and R2 and stores the result into the register R3, right? R1, the contents of R1 and R2 will be added by the ALU, that is arithmetic and logic unit, and the resultant value will be stored into a specified register called as R3, and the same will be moved to the contents of register R3 will be moved to a memory location called as Z. It will be moved to a memory location called as Z. This is how your load and store instruction works. Load in the sense that if the operand is specified in a memory location, the contents of it is loaded to a register using the load instruction. That is what X is the memory location, and moving the contents of this value at this memory location to a register R1. So Y is the memory location. The value at this memory location will be moved to R2 and add the contents of R1 and R2, and the resultant value will be stored into R3, and the same will be moved to another memory location called that. This is how your load and store instruction works. The conventional instruction execution by the processor follows the fetch, decode, and execute sequence. That is a part of the instruction pipelining, right? So now what is that by instruction pipelining contains? It contains three sequences: fetch, decode, and execute. What is that fetch part? Fetches the instruction from program memory or code memory. It basically fetches the instruction from the program memory or the code memory. It actually fetches the value or the code from the memory. So, okay, the fetch part fetches the instruction from program memory or code memory. It actually fetches the instructions, and decode part decodes the instruction to generate the necessary control signals, right? Whatever the control signals that has to be generated, and it is done at the decode sequence. And in the execute sequence stage, reads the operands, perform the yellow operations, and stores the result. Once the decode part is over or the decode stage over, the instruction will be executed by reading the operands and performing the ALU operations and storing the result onto a register or onto a memory location, right? These are the three stages of a pipelining or the instruction pipeline: fetch, decode, and execute. In conventional program execution, the fetch and decode operations are performed in sequence. Both one, that is fetch and decode, will be done in sequence. For simplicity, let us consider decode and execution together, right? So decode and execution will be done, or the fetch and decode will be done in sequence, right? But for simplicity, let us consider decode and execution together, right? They are done in sequence. That is, fetch and decode will be done in sequence, whereas decode and execution will be done together. That is how your instruction pipeline work. During the decode operation, the memory address bus is available, and if it is possible to effectively utilize it for an instruction fetch, the processing phase speed can be increased, right? What you are doing is that memory bus address bus is available, and you can increase the processing speed at this stage. Instruction pipeline refers to the overlap execution of instructions, right? When overlap in the sense that when the one instruction is executing, the second instruction is in decoding stage, and the third instruction is fetching stage. This overlapping of the instruction, we call it as the instruction pipelining, right? Instruction pipelining refers to overlapped execution of instructions. While the current instruction is being decoded and executed, the next instruction will be fetched. If the current instruction is in progress, is a program control flow transfer execution instruction like jump or call instruction. The instruction fetched is flushed and a new instruction fetch is performed to fetch the instruction. If the current instruction is in a in execution, but there is a jump or a call instruction, that is, if there is a branch instruction or a jump instruction, then whatever the current instruction you have it in the memory, that will be flushed and the new instruction will be loaded or it will be fetched. That is what, if the current instruction is in progress is a program control flow transfer. The program control flow transfer instruction like jump or call instruction, the instruction fetch is flushed and a new instruction fetch is performed. So you're performing a new instruction fetch perform to fetch the instruction. You are fetching the new instruction to fetch it. Before that, the previous instruction will be flushed. And whenever the current instruction is executing, the program counter will be loaded with the address of the next instruction. So it is going to have the address of the next instruction. Whenever the current instruction is executing, the program counter will be loaded with the address of the next instruction. It basically contains the address of the next instruction. In case of jump or branch instruction, the new location is known only after completion of the jump or branch instruction. It is known only after the 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 new location is known only after completion of the jump or the branch instruction, because the execution, we don't know what is the next instruction, because you have to finish the body of the jump or the branch instruction. So that is how your instruction pipelining works. Depending upon the stages involved in an instruction, either it is fetch, read register and decode, and execute instruction, access an operand in data memory, write back the result to register, etc. There can be multiple level of instruction pipelining. There are multiple level of instruction pipelining based on the number of stages you are given out. Figure illustrates the concept of instruction pipelining for single stage pipelining. Right, you are using a single stage pipelining here. So what happens in the first step? So look at in the machine cycle one, you are having the PC, that is, you are having the PC, that is the first instruction to be execute the fetch route. And while the PC minus one, that is a next, the previous instruction is in the execution phase, and the clock cycle number two. So okay, so we are execute, or you are fetching the PC plus one. So okay, the next instruction, and execute the PC, that is the current instruction will be get executed. And in the clock cycle number three, you are executing, or you are fetching the PC, that is the current instruction plus the next two instruction, we are executing that. And you are executing the current plus the one instruction, that is called as the execute PC, that is a program counter plus one it is. So that is how your the instruction pipelining actually works. So at for machine cycle one, we are executing the current instruction, sorry, we are fetching the current instruction, whereas we are executing the last instruction, right? We are executing the last instruction. And in the clock cycle number two, we are fetching the next instruction while the current instruction is being executed. The current value of the PC is being executed. Whereas in the clock cycle number two, I'm executing the the PC plus one instruction, whereas I'm executing the PC plus two instruction. There is a program counter value plus the two instruction that I am executing it. So that is how your a single stage pipelining actually works, right? And depending upon the stages involved in an instruction, there is a multiple level of instruction pipelining. That is how many number of things you have it. Here we have only fetch and execute. We have only two stages here, that is fetch and execute. So that's why it is only as it is very much simple one. But if we have multiple stages here, that is to we have fetch, decode, and execute, and write back, and all the things. There are different stages. Then it becomes much complex one, right? So, but here it is very much simple one because we have only fetch and execute. And the next one, it's the application specific integrated circuits, that is the ASICs. Application specific integrated circuit is a microchip designed to perform a specific or unique application, or the unique application that is basically used for. It's a microchip designed to perform a specific or unique application, used as a replacement to conventional general purpose logic chips. It's a sim microchip designed to perform a specific application. It integrates several applications into a single chip and thereby reduces the system development cost. What you are doing is that it is fitted with the different several applications. Uh, Using this several application, you can reduce the system development cost. The ASIC consumes a very small area in the total system, helps in design of smaller system with high capabilities of the functionalities, right? You're developing or you are using these microchips so in a specific area, so it helps in smaller systems with higher capabilities as well as the functionalities. Fabrication of ASICs requires a non-refundable initial investment for the process technology and configuration expenses. Right? Once you start the ASIC, that is application specific integrated circuits, you don't expect anything from the initial investment. You just start stating like whatever the investment you have, it won't assume that it don't return it, right? Once the investment so once you start fabrication, and if you start marketing it, you'll get the values. This investment is known as a non-recurring engineering charge, and it is one-time investment, right? This is just like on what you call it as a research area, you are investing it. If the non-recurring engineering charges is borne by the third party and the ASIC is made openly available in the market, then referred as the application-specific standard product. Once you have the product in hand, even if you start marketing it, right? Then that is called as application-specific standard product, right? So this is what we call it as the application-specific integrated circuits, which are nothing but the microchips designed for a specific application. And these can be these are very small, right, applications, and they have smaller capabilities, but they are small in number, but they have high capabilities as well as the functionalities, right? And the next one is a PLD, so that is called as the programmable logical devices. What is that programmable logic devices? Logic devices provide specific functions including device to device interfacing, data communication, signal processing, data display, timing and control operations, and almost every other function a system must perform. These logical devices or logic devices provide specific functions, including device-to-device interfacing, that is, connecting connecting two or more devices, and the data communication between the connected devices, and the signal processing, data display, and the timing and control operation. This is done by a single system called as the logic devices. Logic devices can be classified into two broad categories. First one is the fixed logic devices and the programmable logic devices, right? The circuit in a fixed logic device are permanent, right? They perform one function or a set of function. Once manufactured, they cannot be changed, right? So the fixed logic devices are nothing but they are fixed in nature, right? Whatever the circuits you have, it is permanent. Once you fabricate it, it is done. You cannot change it, right? So they perform one function or a set of functions, right? They are able to perform one or more functions, and once it is manufactured, they cannot be changed. You cannot reprogram it, or you cannot write anything into the logic devices. And there is something called as a programmable logic devices, PLDs. What is that? PLDs offers customers wide range of logic capacities, features, speed, and voltage characteristics, and these devices can be reconfigured to perform any number of functions at any times, right? At any time, they are meant for they provide the customers with a wide range of logic capacity, features, speed, and voltage characteristics, right? And these devices can be reconfigured to perform any number of any number of functions at any time, right? So they can be reconfigured or reprogrammed so that it is going to meet the demands of the customers. Designers use inexpensive software tools to quickly develop, simulate, and test their designs, right? So these designers are basically developing the software tools to quickly develop the PLDs, simulate them, and test their designs, whether the simulated or the whether the device is going to work correctly if you manufacture it. Then a design can be quickly programmed into a device and immediately tested on a live circuits, right? These simulated devices or the programmed devices can be uh, produced quickly, and they are immediately tested on a live circuit. That is a basic advantage of the programmable logic devices. So okay, so we have two types of the logic devices: fixed and the programmable. Fixed device, which contains the logic device is permanent and you cannot reprogram it or you cannot reconfigure it. So but whereas a programmable logic device, you can reprogram it or reconfigure it, so that whenever the need arises, whenever the customer wants to make new features into that, you can redesign it, right? And you can simulate it and test them, and once the testing is correct, you can fabricate it or you can test it on the live circuit. That is called as the programmable logic device. And there are no NRA cost, and the final design is completed much faster than of a customer fixed logic device, because we have the sophisticated tools. Using these sophisticated tools, we have done most of the work. So this is much faster. That is the final design is once the final design is complete, fabrication is very much, or the testing on a live circuit, it becomes much more easier one. Another key benefit of using PLDs is that during the design phase, customers can change the circuitry as often as they want until the design operates to their satisfaction. This is one more important feature of the PLDs. So these So another key benefit of the PLDs is that during the design phase, customer can change the circuitry as often as they want until the design operates to certain their. So they, because these PIDs has been designed on a sophisticated tools, you can modify the design, and like you can modify it, remodify it. So as long as the customer has the satisfaction. PIDs are based on rewritable memory technology to change the design. The device is simply reprogrammed, right? Once you feel that the PIDs are not according to the satisfaction of the customer, you can reprogram it or you can reconfigure it. That is the basic the biggest advantage of the programmable logic devices. Once the design is final, the customers can go into immediate production by simply programming as many PIDs as they need with the final software design file. So what they have the design file, so they can directly go for productions, right? The two major types of programmable logic devices are field programmable gate arrays, that is FPGAs, and the complex programmable logic devices, right? These are the two programmable, like the logic devices are basically classified into fixed and the programmable. Again, the programmable logic devices, that is PLDs, is again classified into uh, field programmable gate arrays as well as the complex programmable logic device. Let us look at the difference between these two. What is the difference between CPLDs and the FPGAs? FPGA, the FPGA offers the highest amount of logic density, the most features, and the highest performance. Right? They give the logic density. Right? You can put as much logic as you want into the PLDs, okay, and you can also include, right? So they most the logic density you have it, and the more it also supports most features and the highest performance. Whereas the CPLDs offer much smaller amount of logic, up to about 10,000 gates, right? The logic density in the sense the number of gates you can put into the chip, right? In case of FPGA, you can put large amount of gates, whereas in the CPLDs, you can put logic gates, right? Only up to 10,000 gates you can put. The largest FPGA now shipping, part of the Xilinx Vertex line of Vertex. And the largest FPGA now shipping, that is a part of the Xilinx Vertex line of devices, providing 8 million system gates, right? That is, you're encoding, or sorry, you are fabricating 8 million system gates or the logic gates onto a FPGA, whereas but CFP offer very predictable timing characteristics and therefore ideal for critical control application. This is not good. But in case of the FPGA, you can have a maximum of 8 million nowadays with the Xilinx Vertex line of devices. You have 8 million what you call it as the logic gates, right? But whereas in case of okay, we'll continue the things, right? So the difference between CPLTS and FPGA. So FPGA has having highest amount of logic density, that is number of logic devices or the logic kits that you have it. But whereas CPLD has a limited number of logic kits, that is around 10,000 logic kits I have it. And there is one device which is called as a Xilinx Vertex line of devices, which has approximately 8 million system bits, right? 8 million in the sense 8 crore, 8 million, 80 lakh kits in a single chip. But whereas the number of logic kits in a CPLD, it is very limited. These advanced devices offer features such as a built-in hardwired processors, substantial amount of memory, right? Clock management system, and also it supports for many of the largest, very fast device-to-device signal technologies. It also contains these devices or also contains everything, right? Hardwired processors, substantial amount of memory they have it, and clock management system and support for many of the latest very fast device to device signal technologies. But whereas CPLD offer very predictable timing characteristics, and that's why they are used in critical control applications, right? This they can, even though they contain very good features like but the CPLD has good timing characteristics. That's why it is used in critical control applications. FPG are used in a wide variety of applications, ranging from data processing and storage to instrumentation, telecommunications, and digital signal processing. Right? They're used in a very like different areas of the things. So, such as data processing and storage, they are used in data processing and storage to instrumentation, telecommunication, and the digital signal processing as well. But it is almost used in critical applications. CPLDs. CPLDs such as a grinding school runner series also require extremely low amount of power and very inexpensive, making them ideal for cost sensitive battery operated portable applications such as mobile phones and digital handheld assistants. Right. So there is one device they are mentioning it, that is uh, Xilinx cool runner, right, which requires very low battery, which operates on low battery. That's fine. uh, they're they're very cost effective in terms of uh, the power, right, power consumption. So that is the biggest advantage of the right there. It is a basic advantage here is that they are having okay. Let us look at the advantages of the PLDs. The PLDs offer customers much more flexibility during the design cycle because design iteration is simply a matter of changing programming file, and the result of design changes can be seen immediately in working parts, right? So one more flexibility is that design cycle, because design iterations are simply a matter of changing the programming files, right? You are just changing the program files. That's why the PLDs are very much simple as compared to other microchips. PLDs do not require long lead times for prototypes of the production parts, right? They don't require much production time parts, are also as well. They don't need the prototypes as well, because the design is done on a software tool and it is simulated, and once the simulation is correct according to the customer satisfaction, so it directly goes for fabrications. The PIDs are already on a distributor's shelf and ready for shipment, right? So once it is fabricated and tested on a circuitry, and it is ready for what is that shipments. And the PLDs do not require customer to pay large generic cost and purchase expensive mask test sets. PID suppliers incur those costs when they design their programmable devices and able to amortize those costs over the multi-layer lifespan of a given line of PIDs, right? They don't incur more cost on the customers. That's what. And the PIDs allow customers to order just the number of parts they needed, right? And when they need them, allowing them to control the inventory, right? The customers has the flexibility of ordering only those parts which they need it, right?
So PLDs allows customers to order just a number of parts they need it, right? When they need them, allowing them to control the inventory. Only those parts which they need it, they can order it. PLD can be programmed even after a piece of equipment is shifted to a customer. That is one biggest advantage of the PLDs. The manufacturers can add new features or upgrade products that already are in the field. What is that? So once the PLDs are programmed, and if they are working, if they are deployed on a customer site, and still you can reprogram it and you can modify the things, and also you can add new features to that, right? That is what the manufacturers can add new features or upgrade products that already are in the field. To do this, they simply upload a new programming file to the PLD via the internet, creating new hardware logic in the system. This is one more best feature of the PLDs. What they do is that they, even though PLDs are working on a customer site, so what they do is that if they want to reprogram it, or if they want to add a new features, or if you want to add upgrade the products, what they do is that they will do it using the by sitting in a geographically larger distance. That is, they are uploading the new programming file to the PID via the internet, creating new hardware logic in the system. In that way, after purchasing a PLD by the customer, even you can reprogram it. There is no question. There is no question of bringing that PLD from the customer site into the development area, and you have to change. No, you can change the contents, or you can reprogram the PLDs by sitting geographically distance from the customer. So that is what that is all about programmable logic devices. The next one is the commercial off-the-shelf components. What is that? It is called as the cost product. The commercially off-the-shelf product is one which is used as is, right? You just use the things as they that comes with. The cost products are designed in such a way to provide easy integration and interoperability with the existing system components. What you do is that now these products have been developed by someone else, right? And you just integrate those COTS product into your application, or into an existing system components. The COTS component itself may be developed around a general purpose or a domain specific processor, or an application integrated circuits, or a programmable logic device. These COTS components can be developed using any of the things, that is a general purpose or the domain specific processor, or an application specific integrated circuits, right? So what is that commercial off the shelf the products is that you are developing the products, and these products can be integrated into an existing system, right? And check whether these integrated system will be having any of interoperability problem or not. If they have the interoperability problem, right, they will be checked against it. So that is the biggest advantage of the COTS product. And what are the advantages here? They are readily available in the market. This is, oh, what is that? So these COTS products are readily available in the market. They can be purchased in the market at a cheaper price. And the second one is they are cheap, right? They are not they are less costly. Developer can cut down his development time to a greater extent, because uh, these core products are developed much earlier, and they are available itself, and the developer need not have to concentrate on the developing these products, because they are available in the market. What he is supposed to do, he has to integrate those cost product into his uh, his product, so he can concentrate on the major part of the product, reduces the time to market it, right? So what do you guys? So you are saving much of your time, because most of the products are available in the market. You just integrate them into your system, so you can save the time as well, right? All right, this is what the commercial off the shelf components will do it. And Typical example of COTS hardware units are remote control tie for car units, right? You are just using uh, core controllers including the RF circuitry part, high performance, high frequency microwave electronics, and high bandwidth analogs to digital converters, devices, and components for operation at very high temperatures, electro-optic IR imaging arrays, UV or IR detectors, etc. Right? So there are some examples here, right? Remote control tri-car controllers, which is freely available in the market. Not freely, they are available in the market and at a less cost, cheaper prices. Example is another example is TCA type plug-in module available from various manufacturers like Biznet, Freescale, Dynolog, etc. are very good examples of COT products or the COTS product. They are easily available in the market, so you can make use of them and build your own applications. So that is what the commercial off-the-shelf components will do it. And the next one is memory. Memory is an important part of our processor. It's an important part of the processor and controller based embedded system. It's an important part of a processor or a controller based system. And some of the processors or controllers contain built-in memory, and this memory is referred as on-chip memory, right? There are some systems or there are some processors which are having a built-in memory, and these built-in memory are called as a on-chip memory. Others do not contain any memory inside the chip and requires external memory to be connected with the controller or processor to store the control algorithm, and it is called as the off-chip memory, right? There are some processor which don't have, or those who don't have the memory which is built into the system, and for those processor or the microcontrollers, you're supposed to connect the external memories, and these external memories are also called as the off-chip memories. They are called as the off-chip memory. Also, some working memory is required for holding data temporarily during certain operations. There are some, you need to have the working memory that is basically used to hold the data temporarily. So let us look at how your program actually looks like. So, okay, so you have the program memory or a code storage memory of an embedded system stores the program instructions, right? Program memory as well as the code storage memory of an embedded system stores the program instructions. The code memory retains its contents even after the power is turned off, right? Code memory basically contains, it retains the contents even after the power turns off. It is generally called as non-volatile memory, and it can be classified into different types, right? First one is we have the code memory, which is the non-volatile memory, ROM. Flash you have it, ROM, right? Programmable read-only memory and master memory, MPROM. Erasable program EPROM, EEPROMs, and NVRAMs. These are the part of the ROMs, that is code memory. And these code memory are non-volatile in nature. So what is that? They will retain the data even after the power goes off, or if the power turned off. Even after that, the data will be retained, or the code will be retained. So let us start understand what do you mean by the each memory type here. First one is the master memory or the master ROM, which is also called as the MROM. Master ROM is a one-time programmable device. It's a one-time programmable device. Master ROM use of the hardware technology for storing data, right? It is only one-time programmable device. That is, once you write something into the master ROM, so you cannot erase it. The device is factory programmed by masking and metallization process at a time of production itself, according to the data provided by the end user, right? The user will provide whatever the data you want it, and this data will be programmed, or it will be flashed onto a ROM, and it is permanent. It is permanent, and it is one-time process, right? Once the data has been written on the ROM, you cannot you cannot erase it. The advantage, low cost for high volume productions. This is the this is very uh, less costly one compared for the high value productions. The limitation of the MPROM is that, or the MPROM is that inability to modify the device for firmware against the firmware upgradations. Right? If there are any upgradations, firmware upgradation, you cannot make the modification because it is one time, or the one time programmable device. Once it is written into the device or the MROM, so you cannot erase it. So that, or you cannot modify it, or you cannot upgrade it. That is the only limitation of the master ROM. Since the MROM is permanent in bit storage, it is not possible to alter the bit information, right? So every bit that you have stored, it is permanent in nature. You cannot alter it, or you cannot modify it, or you cannot delete it. That is what we call it as the master ROM. And mask down, different mechanism was used for the masking process of the RAM line. Creation of enhancement or the depletion mode transistor through the channel implant. There are some methods which are used in for MROM. So the creation of an enhancement or depletion mode transistor through channel implant. This is one method which is used to write the contents onto a MROM by creating memory cell either using a standard transistor or a high threshold transistors. Okay, using memory standard transistor, high threshold transistor, you can write contents onto the master. In the high threshold mode, right, the supply voltage required to turn on the transistor is above the normal ROM IC operating system voltage. Right, in the high threshold mode, what you're doing is that you're passing high voltage, which is required to turn on the transistor is above the normal IC operating voltage. It is more than the ROM IC operating voltage. You are supplying the voltage, so you are writing each bit on the MROM. This ensures that the transistor is always off and the memory cell stores always logic 0. Right, when you do that one, that you when you want to write 0 into that, so what you are doing is that you are just uh, passing high voltage, and that will ensure that the memory cell stores always logic 0, which is nothing but all the bits are set to 0. So that is how we can use the master ROM. Master ROM is nothing but a one-time programmable devices. So once the bit has been written, it will not be altered, it will not be changed. Okay, that is what for the today's class. In the next class, we'll continue with the prompts, right? That is a programmable read-only memory. Okay. You have any questions? Do you have any questions? Do you have any questions?
No,
No. ಕೇಳ್ತಾ ಇದ್ದೀರಾ?